Good morning, everybody. Thank you very much for the kind introduction. And I'm very happy to be here. For me, this is almost like springtime or summer. I know for you it's winter. Relative to Canada, this is hot for me. So thank you very much for inviting me. And I want to try to convey something which is very important for everybody, for you in this hall. Even if you're not interested in my talk, at least the topic, it's necessarily of interest because it's about your own self. And I hope to convey some idea what your sense of self is, how that is related to your brain, and how that is relevant for psychiatry and to understand psychiatric symptoms. I start with something, you already see this here on my screen, a very famous movie, Frankenstein, highly recommended for download on YouTube. And and the question of my talk is really, how is it possible that purely neuronal activity transforms into mental activity? Like you experience a sense of self, I hope that you're conscious, and this is necessary to understand psychotic symptoms in all kinds of disorders, and I will show you later. And what we haven't understood in psychiatry yet is really how and why are these symptoms generated, meaning the mechanism underlying these symptoms. Just makes a comparison to diabetes as an internal medical disorder. There you know very well, if you're very hot, and finally they measure your glucose, and you know that the various symptoms are related to the glucose, and that in turn is related to the level of insulin. So there's a specific mechanism which we understand, and that allows us to properly therapeutically interfere. This connection we haven't understood in psychiatric symptoms. And I start with two models of the brain, sort of as a background, which is very important to understand the data I will present and the conclusions I draw. First, the brain is like a car. So this is basically the model of our brain we often presuppose. As you can see, this is not a Ferrari or an Italian model. This is a Japanese model because I cannot afford a Ferrari, unfortunately. So where's the analogy to the brain? So when you push the gas pedal, you push it very strong, you get a lot of speed, particularly with the Ferrari. Whereas if you push the gas pedal a little weaker, the car will be much slower. Meaning, there's a direct linear and proportional relationship between the strength of your gas pedal push and the speed your car will drive. And this is a model of the brain which is really very much presupposed also in our times and very dominant. So it's a pure mechanical linear model. I'll explain you. Finally, I get something from Italy, the Colosseum from Rome, here. And this is a stimulus which we use to induce activity in the brain, either in brain imaging or also on the cellular level, where we use all kinds of stimuli to induce activity in the brain. And then we see what we usually describe as stimulus-induced or task-evoked activity. And what is important that we assume a direct linear relationship between the stimulus and the task-evoked activity. So meaning this one is sufficient for this one. Same as the gas pedal and the push and the speed. However, that leaves out something. First, we all observe inter-individual differences in our data. These are bad. They are supposed to be averaged out, and the reviewers will criticize you. However, that's one thing which is not considered, because you should not have inter-individual differences if you always present the same stimulus. And second, even more important, it leaves out consciousness and self, because neither consciousness nor self come with specific stimuli or contents. They are attributed or associated to the stimuli or the contents by the brain. So the brain does something here, which is very special. So this model is very well for certain cognitive functions, affective functions, sensory functions. However, it seems to be problematic when it comes to subjective features, sense of self, consciousness, and psychiatric symptoms. So, the alternative, the brain, is not like a car. So even the best of all your Ferraris will not work for the car. Sorry. So imagine you're stepping out of this building and your car is moving by itself in all kinds of spatiotemporal trajectory. It has spontaneous movement. This is not yet a self-driving car by Google or Tesla. Yeah? So there's no driver in there, and like a tennis player, I'm a big fan of Roger Federer, so when he's awaiting the service, he's doing certain movement and try to position himself for the service from Rafael Nadal. So, and that's exactly what our brain does. It continuously moves in certain spatiotemporal trajectories. And that has major implications. So here now, the brain approaches the stimulus on the basis of its own spatiotemporal trajectories. And what we observe here as stimulus or task-evoked activity is a mixture or a hybrid of the interaction between the two. And this interaction we haven't really understood. And that interaction is necessary to be understood because that's where it's decided whether consciousness or self will be associated with the stimuli. And if you have changes in the spatiotemporal structure here itself, it might affect all subsequent function, cognitive, affective, etc. functions. You will see this later in my talk. So, I will go with this model of the brain, sort of where I highlight the spontaneous activity and its spatiotemporal structure. There's a lot of investigations into what is called resting state and spontaneous activity. However, the function and the role of the spatiotemporal structure of these spatiotemporal trajectory or the spatiotemporal dynamics is not well, if at all, understood. And I will show you some data, and that's the main claim, that this spatiotemporal structure is central for mental features like self and central for psychiatric disorders, specific psychiatric symptoms. So if you want, you could also rename the talk of my title in this way. Where do the symptoms come from? We don't know yet. There I claim it's a spontaneous activity in itself, and it's a spatiotemporal structure. That's why I speak of a spatiotemporal psychopathology. Let me develop. So my talk has two main parts. First, I show you and present you some data about the sense of self and its underlying spatiotemporal structure. And secondly, I will present you some data from a psychiatric disorder, bipolar disorder, where the data support a spatiotemporal view on specific symptoms. And I will not provide you therapy data, but I don't need to tell you that if we understand the mechanisms, then we have really ways to interfere with to more targeted and individually based interfere with the corresponding correlates. Let me start with the first part, the self. For that, we need to understand again, when I speak of time and space, I mean not a particular point in time and space. What I mean is the continuous dynamics of time and space. Go back to your Renaissance heritage. Leonardo da Vinci was a master in painting the dynamics of time onto a two-dimensional surface and into three-dimensional space. When you look at his paintings, they really flow. There's a dynamic in there, particularly the background landscape, and that affects the person in the foreground. It's unbelievable how he does this. So he's a real master. So that's what I mean by time and space, dynamic. And that's what you see here. And your brain is an organ of nature. And so it does exactly the same what nature does. It continuously constructs time and space. Yeah? And you have that, you can measure that in terms of certain frequencies. So it continuously fluctuates, and that fluctuates in different frequencies, either a little bit faster as in gamma or beta frequencies, or very slow as in fMRI. And I want to draw your attention particularly here on the very slow frequencies. When you're doing EEG or even cellular recording, you're in a much faster frequency range. You are up here when you do cellular recording. However, what we measure in fMRI is this, the very infra-slow frequency range from 0.01 Hertz to 0.1 Hertz. You don't need to remember that, but it's extremely slow frequencies, long cycle durations, and what is even more important, these guys are much more powerful than these ones. So imagine you're here going to the Mediterranean Sea, you see a fast, quick wave, it's fast and quick, it has not much power. If a slow wave comes, it's spatially much more extended, and it has huge power and will just push you back to the beach. Yeah? It's probably only happened to the one German who now swims in the Mediterranean Sea at this point of the year. Yeah? And this is exactly what happens in the brain. So you have these different frequencies, and you can see this, for instance, here. These are raw data from fMRI. The different frequencies are also coupled with each other, cross-frequency coupling. I will not go into that. And what is important here, you have much more power in the very slow frequencies than in the faster ones. And that you can say is a scale-free property. What do I mean by scale-free? This is very important. So just look at me here, over there. This is the same person. I hope so. But this guy is much larger than this one. But it's still, there is self-similarity between this one and this one. So that means we're scale-free self-similarity. There's a different spatial scales, but similar. Exactly the same with these different frequencies. They're sort of self-similar, but across different frequency ranges. And scale-free properties are central, so they provide a certain temporal structure to the brain. Now, keep that in mind. Remember here, now we go to the sense of self. So, why is that important? When yourself, remember just here, so now what we said, the main assumption is that the spatial and temporal features, the way the brain constructs its own time and space, are central for mental features. And that's exactly now what we're trying to test here. So one of my former students, Ziru Wang from China originally, he came up with the idea of saying, okay, we try to correlate and link the scale-free properties of the brain's spontaneous activity to self-consciousness. And that's exactly what he did. So first, he measured the spontaneous activity in fMRI, and then he, for each, for these central regions, this is the medial prefrontal cortex, posterior cingulate cortex, typical midline regions. He plotted the power spectrum, and you can see this here. These are the frequencies from fMRI. Here's the power, and you can see there's much more power in the very infra-slow frequencies when compared to the faster one. Remember the example with the wave, the slow wave, and the slow wave and the fast wave when you swim in the ocean. And what you can also see that each line is one subject. So when you look at these data in the traditional way, you say this is a catastrophe. Why? Because there's extremely high inter-individual differences. You say, oh, bad data acquisition, a lot of noise. No, this is an intrinsic inter-individual differences. Why? Because each of your power spectrum in each of you is very different. Because you all grew up in different way, your spontaneous activity is, and its temporal structure is strongly experience dependent upon its respective environmental context. You grew up in Italy, I grew up in Germany, now I'm in Canada, so our power spectra are very different. Yeah? And I'm sure my power spectrum has changed when I moved from Germany to Canada. So I will not go much into this experience dependent, but it's very important for psychiatric disorders. Yeah? So, and now we say, or maybe how are these curves related to your sense of self? And that's exactly what you see here. So we applied a self-consciousness scale where you measure different aspects of yourself, and also you can subdivide into private, public, and social scores. So whether you're a more social person, or whether you're very public, or whether you're more introvert and private. And what was interestingly that the degree of scale-free activity measured here by the power law exponent only predicted the degree of private self-consciousness, meaning the higher your power law exponent, the higher your degree of scale-free activity, the higher your private self-consciousness. So that, for me, these results at the time were very exciting because they provided a first direct link between the temporal structure of the spontaneous activity and the sense of self or self-consciousness. Meaning, the self may not be a higher order, exclusively a higher order cognitive functions, as it is often conveyed from philosophy, also transmitted into current neuroscience. It has a very basic spatial-temporal basis. And so now, why is that important for you as a psychiatrist? So here I work together with Andrea Scalabrini from Milano and Katie, and he is very interested in personality changes, personality disorders. And one of the features is obviously the narcissism. So now, if that really holds, that scale-free activity is related to your sense of self, then you would expect that people with high degree of self-focus, like in narcissism, should have higher scale-free activity. So here he investigated a sample of healthy subject group with narcissism scale and see how that is related to both spontaneous activity and task-evoked activity. I will show you some of the main results on this. So we had a paradigm on the anticipation of touch. We did this together with Katie. And what you observed that during the anticipation of touch, as expected, the right insula was activated, particularly during animate targets. So this is task-evoked activity. And what is important, that the degree of insular activity directly correlated with the sub-item of the narcissistic grandiosity in the scale. And which is relevant, the higher your degree of narcissism in the healthy subject, the less response to external stimuli in the right insula. So what do you infer from that? Unfortunately, we did not measure the perception, but what you can infer from that rather than perceiving the external stimuli, the balance in the perception is shifted more towards the internal self. They have less response to the external stimuli, so they perceive the external stimuli less, and in turn, they're more focused upon their own self and perceive the external stimuli only through their own self. And I think this is very closely to clinical reality. So for further experimental testing in the next step, he would probably need to do, let's say, he would need to measure the stimulus-evoked activity and then also the perceptual activity, the perceptual intensity on the level of consciousness. Now, in addition, he did more. He also investigated the spontaneous activity and how that in turn is related to narcissism and task-evoked activity. And I walk you through the slide. So here is the task-evoked activity, and interestingly, that was negatively somewhat related here to the power law exponent, but particularly important here is this relationship, that the higher your power law exponent, the higher your narcissistic grandiosity. So this is exactly what, remember, we predicted. The higher your scale-free activity, your power law exponent, the higher your degree of self. And that's exactly what you see in this group of subjects. And that means the power law exponent, the scale-free activity, remember the slow frequency is particularly dominated by the very slow waves. So that means, and I draw your attention to the next slide on this, that if the narcissism people with high degrees of narcissism show higher scores in the scale-free activity, that means they seem to have relatively more power in the slow frequencies. So maybe they're more internally focused because they're too slow internally to react to the fast external world. Because when you have to react to the external world, it happens fast, and meaning you need faster frequencies in your brain to pick that up. If, however, the power is more tilted towards the slower frequencies, you may be too slow to pick that up. So ultimately, it might be a temporal disbalance between the brain's slow inner time / the time of the internal self and the fast time of the outer world / the external stimuli. And that can be tested. Yeah? So this is a hypothesis derived from these data. Now he could, in the next step, individualize the resting state, individualize the frequency of the stimuli, and he could directly test it. The predictions are clear. After that, if that really comes out, then it's clear what you need to do. You need to fasten up the inner time of these people that they can betterly react to the external stimuli and shift their focus from the internal self to the external self. So maybe, as I provocatively put here, maybe there's a temporal basis to the narcissism's psychological features. So, I hope that gave you some idea that we approach the sense of self not in cognitive terms. The self is not about certain contents, because the contents continuously change. Tomorrow, you have other contents related to yourself than yesterday. However, despite the continuous change in contents, you nevertheless experience a continuity in your sense of self. And that continuity seems to have a temporal basis, particularly by the slow frequencies. So despite all the changes, nevertheless, there's a self-similarity. Yeah? Despite the different scale over there, now I look, I still can see this guy is me. If I wouldn't have that self-similarity, then I would suffer from multiple personality disorder, or, in this case. But it holds it together. So it's a temporal basis which might give you a certain temporal continuity, which in turn is central for your self-continuity, and probably also, over the long time of a lifetime, a personal identity. So, and I mention that because, as you know, as a psychiatrist, it is exactly these processes which, in many patients, are altered. There is no self-continuity anymore. The temporal continuity of the sense of self is altered. That's why, as you see from my accent, I'm originally from Germany, that some early psychopathologists said that psychiatric disorders are basic disturbances of the self. And I could not agree but more. And I show you now some of that. Why do we assume that? The self is strongly encoded and included or contained by your spontaneous activity and in spatiotemporal dynamics. We have many more data on this. Much more will come forward on, will be published on this. So, meaning, and if this spatiotemporal dynamics of the resting state is altered, it implies that your sense of self is also altered, including your sense of time and space. And that's exactly what we see in psychiatric disorders, and what phenomenologists, the earlier one, Minkowski, for instance, described beautifully, and I'm sure that Josef Parnas will add some more descriptions to that too tomorrow. The question is, where do these abnormal experiences of self, time, and space come from? And that's why I say that's where you need the spontaneous activity and its spatiotemporal structure. So I want to give you now two examples on bipolar. So this is work you see, I have strong affiliations here with Italy. This is work we do together with Genova, with Matteo Martino, Paola Macchiocalda the first, and Mario Amore. You see them all here as authors on the paper. And they really opened my view for bipolar disorders. And now I see all these bipolar patients. And it's, as you all know, bipolar patients is not just bipolar, it's also self-disorders, personality changes. They're very colorful people, as you all know. So here we focused on another measure, on another temporal measure of the brain's spontaneous activity, mainly neuronal variability. What do you mean by variability? So usually what is measured in fMRI is usually the amplitude, so the degree to which a signal is high or low. However, you can also say that that amplitude changes from time to time. And this is the variability across time. More formalized is the root mean square of the amplitude. And so in particular now when you translate this into the temporal domain, what neuronal variability indexes is the speed of time. If you have more change, there's a lot of speed. If you don't have much change, consider a depressed patient for whom nothing changes, time stands still. So the speed, the neuronal variability, the degree to which a signal can change over time, can give you an index of the speed of the brain's inner time, of the neuronal time. So, and we investigated this here, and we particularly focus on two networks. Here, the red dots are the default mode networks. This is the anterior cingulate, ventromedial prefrontal cortex, posterior cingulate, precuneus. The experts among you is typical default mode network. And here the blue spots are the sensomotor network, premotor cortex, motor cortex, sensomotor cortex. And particularly here we focus on the neuronal variability, and I show you here the healthy subjects. Here these are the different regions of the default mode network. These are the different regions of the sensomotor network, and you can see that the variability is higher in the default mode network. And so when you take that sort of as a balance or as a ratio, you can see it's tilted towards the default mode network. Now let's go to the depressed bipolar patient. This is, I must admit, they collected a very unique data sample, which is worldwide unique because it really includes depressed, manic, euthymic patients, and also in part intra-subject comparison. So you can see here that you have much higher variability in the default mode network in the depressed patients, and in the sensomotor network you do not have much variability. And then you can see the balance is tilted towards the default mode network. Now, consider mania. It's exactly, so here the variability is strongly reduced, and here it's relatively enhanced in the sensomotor network, so you have this one. And you can see this and this are extremes of this. So it goes either tilting towards the DMN or tilting towards the sensomotor network. So then when you calculate the balances, look up here, particularly here in the default mode sensomotor network, you have exactly this one. You have an extreme large balance in the depression. You have the mania, the opposite, and you have the euthymic and the healthy subject in between. So this is, I'm a big fan of inverted U-shaped curves where the both extremes are usually the psychiatric disorders, and you can see this clearly here. The depression are at one end of the extreme, mania at the other end of the extreme, and the healthy are sort of in the middle. So now the question, why and how is that relevant for symptoms? Next step. So then they also correlated the ratios with the respective scales, with depression symptoms here, Hamilton Depression Scale, here with the Young Mania Rating Scale, the manic symptoms. And as you expected, the higher the ratio is tilted towards the default mode network, the more depressed symptoms. And then the opposite, the more it is tilted towards the sensomotor network, the more manic symptoms. However, what you can see here and they probably hate me for this one because I know that they're in the audience, as nice as these data are, and I think they're a major progress in the psychiatric literature, however, we're still missing something. What you as a clinician want from us, from the brain imaging people, is you want an individual prediction. But here you can still see that the same value can be associated either with the euthymic, here's the brown, the yellow, the manic, or depressed subjects. So something we are missing in the imaging data, and we're working on this. Because you need 100% distinction between healthy and pathological subjects. It's the same what you have in the diabetes in internal medicine. How now is that related to symptoms? Variability. Remember that what we measured, the fluctuation of the amplitude. And you know that in every region you have a certain threshold which in the degree of activity which needs to be surpassed in order to elicit an internally generated activity. Let's say, if the activity in motor cortex surpasses a certain threshold, you initiate a movement, like me now. Yeah? However, if you do not have much activity change, you have a much lower likelihood of surpassing that threshold. Meaning, you will not generate much movements, meaning you will not walk much, you will sit still in the corner. That's exactly what you see in depression. Yeah? So you have less activity, less amplitude changes, lower likelihood of surpassing the threshold, and internally generating movement, meaning you sit in the corner, psychomotor retardation. However, you may remember that the variability changes were much stronger in the fault mode network, meaning they have much higher likelihood of internal generation there, meaning the spontaneous thoughts are much increased. That's exactly what you describe as ruminations. In mania, it's the opposite. You know, the manic patient runs around like crazy and initiate a lot of movement, increased variability in the motor cortex. And whereas in DMN, you had much less variability, so meaning they may not initiate much internal thought. So after this finding, I asked my patients, what do you think during the mania? And almost all said, we don't think at all. So this is one of the ideas, and I hope we have other data sets published and in preparation, where we can really say that maybe the spontaneous spatial-temporal structure, its spatial-temporal features, temporal features, spatial features, translate into psychopathological symptoms. Meaning, I show you this one, that the cognitive, affective, sensory-motor, and social functions are organized in an abnormal spatial and temporal way. If your spontaneous activity shows an abnormal spatial-temporal structure, your subsequently generated cognitive or affective functions will be affected by this. Yeah? That relationship, those relationships, we haven't understood yet, but we are working on this. So this ultimately amounts to this, so I leave this out for reasons of time, that the spontaneous activity, you have a certain experience of time and space and of your internal self and the world. So meaning the basic mental features, self and consciousness, are intrinsically spatial-temporal. It's about the spatial-temporal organization coming back from here. And that in turn, if you have altered spatial-temporal structure here, you have abnormal experience of time and self here, and then you have psychopathological symptoms. I showed you this one. I haven't showed you this one, because this is central. This is what the old phenomenologists, old and current day phenomenologists describe. And that is ultimately the mediation to this one, which is about cognitive affective functions. Let me come back to one investigations, again, same group of patients, again, neuronal variability. So here we particularly tried to link neuronal data to phenomenal features. So I like to describe this as a neurophenomenal approach methodologically, because you link third-person data to first-person experiences. This has also been described as first-person neuroscience. However, what exactly makes this transition or transformation possible? As I said, nothing mysterious. In Canada, I know very well, we have frozen water, we have liquid water, we have steamed water. Depending on the context, they transform into each other, but it's all one and the same. Exactly this transformation from the neuronal and phenomenal level is the common currency, what I suppose and the data suggest are the construction of time and space. So this is really the common currency between brain and experience. If so, you need to investigate both on the level of the brain and on the level of experience. Yeah? So, look into the phenomenology, the subjective experience of bipolar disorder. Thomas Fuchs made a beautiful description of this, and Giovanni Stangelini had some very nice papers on the phenomenology of depression, and he also on schizophrenia together with John Cutting. So what you see here in depressed patients, you see that the inner time stands still. You all know this from your patients. That's what they tell you. Nothing happens, nothing changes. It stands still and it drives them crazy. They're fully aware of that, but they cannot change it. Yeah? And what is also important, they are out of tune. They experience the outer world as too fast. I remember when I interviewed a young girl in China, she was severely depressed, and she told me she was completely mute during the depression. And afterwards, she told me that she didn't talk because she knew that her mother was talking in normal speed, but for her it was too fast. She couldn't cope with it, and that's why she said it made no sense for me to talk. So there was a discrepancy between inner time, too slow, outer time, too fast. In mania, obviously, it's the opposite. The manic patient is extremely fast, and we are too slow for him. Of course. And when you have the feeling that the other guys are too slow, what do you become? You become impatient, angry, and that's what we see. It's very normal. So it might be a temporal thing. And what is important, and I already indicated that in my example, that we take our inner time speed as a reference or standard for the outer time speed. So we perceive the outer world, the speed of the outer world, in terms of or relative to our inner time of the self. Yeah? So if our inner time is too slow, we experience the outer time as too fast. If in contrast the inner time is too fast, the outer time might be too slow, even if objectively the outer time is in both cases the same. So this is very important. So it's really, if you have too fast inner time, you experience the outer time as too slow, and the other way. And usually in healthy subjects, it's quite well synchronized with each other. Yeah? So if you have problems following me, your inner time might be too slow, maybe because it's early morning and you're still tired. Yeah? Or maybe I'm simply too slow for you because you're Italians, you're fast, and me as a German from Canada, I'm too slow. Yeah? Possible. So we need to do a fMRI in you. So how now do we link this to neuronal activity? Again, remember, neuronal variability change in the amplitude. If the amplitude changes a lot, you probably have a high neuronal speed. High change, high speed. So maybe neuronal variability is a very good measure of the neuronal speed or the speed of time. It's a neurotemporal basis. Now, there have been a lot of investigations that linked the inner time perception to the somatomotor network. We had this before. And then we thought, how do we perceive outer time? Because outer time must also be processed by our brain. So where do we first process in our brain the events, objects of the outer world? In the primary sensory cortex, for instance, in visual network. So basically, we took the visual network and the spontaneous activities, neuronal variability in this network as a proxy for outer time, and for inner time, somatomotor network. And here we calculate again the balances. You see here the healthy subjects, they show a slightly more variability in the visual network, in sensory-motor network, but more and more balanced. And here it's very nicely, you can see the exact opposite. In depression, sensory-motor network has not much variability, meaning low speed of time, whereas in visual network, a lot of variability, fast speed. Manic, you see exactly the opposite. So now, then we plotted again the ratio. Remember this picture. We take our inner time as a reference or measure or standard for the outer time. How can we transfer this on the neuronal side? We plot the visual network against the somatomotor network as a proxy for inner time. This is what I plotted here, and you see that the balances are hugely different. In mania, the sensory-motor network dominates, shows much more variability, meaning inner time is much faster relative to outer time. And that's exactly. They experience the outer world as too slow when compared to the inner world, which is much faster. Depression, the opposite, and in healthy subject, intermediate. So, of course, now you say, what is missing here? We need actual time perception data. We're working on that. Then we correlate that with the symptoms. As expected, the ratio, I don't go into detail, but I show you these beautiful figures, which Paola and Matteo did. Here you see in the healthy subject, you see variability in sensory-motor networks, visual networks, somewhat balanced. Inner and outer time are somewhat synchronized. If your variability in sensory-motor network is too slow, your inner time is too slow, and you consecutively experience outer time as too fast. Depressed patients are too slow for the world. Mania, it's the opposite. Increased variability here, decreased variability in the visual network as proxy for outer time. They're too fast for the world. And that's exactly, and then imagine that desynchronization, which Fuchs described on a phenomenological level. Here we can show it on the neuronal level. I come to my last 2-3 slides. What does this imply for our future of psychopathology? Because ultimately, this conference is about psychopathology, and I saw in your website that you had Jaspers in the background. And as you see, I'm originally from Germany, and I did my residency part in Heidelberg, so I grew up a lot with the different forms of psychopathology, and I'm very much tuned to it, and they guide my neurobiology. So Canada, where there's not much psychopathology, is... so here, what I showed you, that the spontaneous activity and many other data translate into subjective experience of time and space. So I argue that this mental features, phenomenal features, subjective experiential features are spatio-temporal features, construction of time and space. And I'm sure, and that in turn, if this construction of time and space here is abnormal, you have an abnormal experience of self and an abnormal experience of time and space, and consecutively, your cognitive, affective, sensory-motor functions are abnormally organized in spatio-temporal terms. And that's exactly what we see. When, for instance, you have too much slow frequencies and not enough fast frequencies, your working memory, which usually operates in the theta 5 to 8 hertz, might be dysfunctional because it has not the fast frequencies it needs. Yeah? So there might be a temporal basis on cognitive symptoms. So, and that might also explain the strong overlap between resting state, spatio-temporal organization, and self might explain what the early psychopathologists already knew very well. Psychotic disorders are basic disturbances of the self, and the self is spatio-temporal. And that also yields novel ideas for therapeutic intervention, because then you would intervention temporally or spatially, or probably both. So this is why I like to speak of what I call spatio-temporal psychopathology. You know, psychopathology is an old discipline in USA. In North America, it's basically dead because everybody speaks just about biology, so I'm considered a strange German guy, because for them it's just biology. Yeah? However, what they don't explain, how the biology translates into psychological symptoms. And this is nothing mysterious, what I'm saying here. It's just biology. Yeah? So that's why I like to speak of spatiotemporal psychopathology, and we published various papers on that. And briefly, so I did not go much into the world-brain connection, the experience dependence of the spontaneous activity, which would be yet another talk, but it goes from the experience to the different symptoms. So from my point of view, I would consider spatiotemporal psychopathology as sort of as a basic framework, as the overall arching framework for different forms of psychopathology, phenomenological psychopathology, existential psychopathology. There was also an interesting structural psychopathology around in my Heidelberg times, cognitive, descriptive psychopathology. So these are not invalid, but these describe distinct aspects, remember, the different levels. But the framework for that, so I would argue phenomenological features are spatiotemporal features. For the ADOC, for the novel classification, I would argue we need spatiotemporal classifier to distinguish the different disorders, and we're working on these things, that different spatiotemporal measures distinguish different spatiotemporal, different psychiatric disorders. And that in turn then yields the psychopathological symptoms. And my hope is that this way of how the brain spontaneous activity constructs its own time and space can first unlock the brain itself, because we haven't understood how the brain yields mental features. And second, it gives us a new way of understanding the mechanism of psychopathological symptoms, and that in turn gives us new ideas how to systematically and individually interfere in therapeutic respect. Thank you very much.
Thank you, Georg. It's very, very interesting. It is a new idea about the neurospatial psychopathological mind. So we have no time because it's a lecture, a key lecture, so we don't have a discussion.
Okay.
And thank you for your speech.
You're welcome.